Hi, I'm Ashwani, and in this video, I would like to implement the reinforcement learning from human feedback algorithm. So what that algorithm is, it allows a large language model, which has been pre-trained on internet corpus to kind of predict the next token in the sequence of tokens so that it becomes kind of like an autocompleter, but then what turns that autocompleter into something like a chatbot, which rather than just completing what you write, it responds to you, it answers your questions. So reinforcement learning from human feedback is the algorithm that allows one to fine tune that autocompleter large language model to kind of behave like a chatbot. So let's just look at the things that we'll be covering today. So, as I said, reinforcement learning from human feedback, or RLHF in short, is the technique that converts an LLM from just being an autocompleter to a chatbot. And now the first question is, why don't we just kind of collect a data set of question and answer and train the pre-trained LLM model in the same fashion that we did the pre-training on this new question answering data set? And the answer to that is, if we just train the model to predict the next token, it kind of forces the model to produce the response in a very specific way. So the feedback that the model receives is per token level. So if you ask a human a question, um, even though they may answer it correctly, but the way they answer it may differ. But this supervised fine-tuning technique forces the model to kind of respond in a very specific way by giving feedback on each of the tokens, what the next token should be that it should produce. So how RLHF differs is it delays that feedback to the end of the response, and then we kind of distribute that reward across the entire sequence of tokens produced by the model. And how we do that? So we kind of first uh, do a supervised fine tuning on the question answer pair so that the model kind of learns what how it should respond to the questions. So rather than responding with another question to a question, it could learn to actually give answer. But then how do we judge the answer that the model produced was good or bad? So we train a reward model that kind of mimics the how a human would uh, rate an answer. If the model produces a good answer, then reward model would take the that question answer pair and give a positive reward or a negative reward based on whether that answer was preferred or not. So now in total, there are three stages. So first we do supervised fine tuning, then we do reward model training, and finally we do the PPO training. And in this video, I would like to cover each of these stages, and I'll be kind of implementing each of these stages in Google Colab Notebook. So I'll be following these three papers to implement each of these stages of the overall algorithm. So this was the reinforcement learning from human feedback paper. And if we scroll down, so this shows all of those three stages or steps. The first step is the supervised fine tuning, where we have a human labeler who writes the answer to a question, and we kind of collect that question answer data set, and we train the large language model auto-regressively, like how we do the pre-training. In the same way, we just train that model on this specific data set that we created. Then we kind of have another version of the pre-trained language model and feed that a set of question answer pair and ask the model to rank which question answer pair is preferred over the other. And over time, this reward model learns to rate question answer pair which are preferred by human better than the ones which are rejected or not preferred by the human. In this video, because we don't have the data set of chosen and rejected question answer pairs, instead, so what we will be training, we'll still be using large language model as the backbone, but on top, we'll be applying a reward head, which would just output 0 if the response is having negative response or a positive response. So it kind of would be categorizing the response rather than ranking the response. Then the final step is the PPO, where we'll be taking the SFT model trained in the first step and the reward model trained in the second step to kind of guide this whole training. So PPO is a reinforcement learning technique. And the way I see reinforcement learning, at the end of the response, we have a reward. And reinforcement learning, what it does, it just kind of distributes that reward to each token. So it's kind of a way to convert a delayed reward into a per token reward. That's all reinforcement learning is. Let me just go back to that slide we were looking. So what I won't be covering in this video would be the building of the actual large language model and the associated tokenizer. So there are a lot of videos already on YouTube that cover these topics. So, and I will link a few in the video descriptions. Notable among them are from Andre Karpathy, so I'll provide links for those. Now, the way the supervised fine-tuning works, so let's say we have a custom data set. It might be some prompt plus responses, or it might be a question answer, a data set of question answer pairs. So what we do, we take the whole prompt plus response as a single sequence and feed that to the large language model and ask it to produce the next token in the sequence. And the way we feed it, we apply some masking so that when it is predicting logit 1, it, it won't be able to see token 2 or any other tokens. And when it predicts token 2, it doesn't see token 3, and so on. And to calculate the loss, what we simply do, we compare the logit. So logit is just an unnormalized probability distribution across the entire vocabulary. And to compare, we apply a softmax on the logit to convert this into a probability distribution, and then we apply a cross entropy loss between the logit and the tokens that we feed to the model. So before delving into other stages, so let's just implement the SFT first. Okay, so here, in order to not implement the LLM and tokenizer from scratch, I'll be using the library from Hugging Face called Transformers. And that library already has quite a lot of large language models. So we can use the one we need. In our case, we'll be using the GPT-2 model to train on our custom data set. So let me just initialize the model and the tokenizer. So I also have Gemini autocompleter on. I'll leave it on for now, but if it turns out to be too annoying, and then I may actually disable it. This generation looks good for now. Then all we need to do is to set a model name, which will be GPT-2 for our case. And then what we simply need to do is to initialize a tokenizer from pretrained, and we'll be using a pretrained tokenizer model. So both of these look good to us. So let's just run it, see if it works. Then to get ourselves a bit familiar with how this tokenizer works, I'll be walking through how we use the tokenizer. So let me just create a new section, tokenizer, testing the tokenizer. And first step would be to encoding. And so the way we can, so let's say if we have a text, say, hello, this is Ashwani. And to convert that into tokens, we can run it through tokenizer text, and these are still loading. Let that run, and then we just print whatever comes out. So what we get is not just the tokens which are here. So these tokens represents these words, and the way to visualize this is by, if we take this string and pass that through the tokenize this app tick tokenizer. So in this case we are using GPT-2 model. So we set the model to GPT-2 and we pass this string, and we can see these are the tokens and how each word is broken down into different tokens. So in this case, my name has been broken down into 3 tokens, and comma gets its own token. And you notice that space plus this have been tokenized as 428. So it's not just this, but the entire space in this. And these tokens, actually, you can see that they match with the ones that we got out of this library. So let me just paste them here, and we can see that these do indeed match. Now, attention masks are uh, just the words which are kind of valid words. And so let's say if we have a batch of sequences that we're going to be feeding to the model, so the padding tokens will have attention mask set to 0, but all the other tokens will receive an attention mask of 1. So it's kind of a way for us to feed sequences of varying length to the model. Now, once we got this, we can also apply decoding step. So the way we apply decoding, and so we take these tokens, tokenizer dot decode and tokens, and we just feed the input IDs, and we just print that, and we get back what we encoded. Now, so this is for one sentence, one text, but we can also have a list of texts. So let's say we have, hello, this is Shwani, or this I have a dog, and I also have a cat. So let's say we got these three texts in a list. Now we could directly pass these through the tokenizer. So we just pass it to the tokenizer and we hit enter. And instead of getting a list of input IDs, we get a dictionary, which again has those input IDs and attention mask as the keys. And rather than producing just a list of tokens, it's a list of lists, and each list is containing the tokens corresponding to each of the sentences. And now to get back the original texts, what we can do for, so we haven't assigned this to, so let's say tokens object, and we rerun it so that it gets assigned. Then we take one tokens in tokens object input IDs, and we decode each of the tokens individually, and we get back the each of the sentences that we encoded. So that's working with the list of text. Now what we would like to do is to work with a data set. So let's just define that. Working with data set. Now to get our data set, we'll be using another library. It's called Datasets. This is also from Hugging Face, and it doesn't come pre-installed in Colab, so I'll have to install it. This line should install that, and let me just hide this output. We don't need this. Then in order to load a data set, we can use loading a data set. So we can actually import from the datasets library, import load dataset. And in our case, the dataset that we'll be working with is going to be an SFT2 dataset, which is from the Stanford So that's the data set that will be working. And it's got three splits, so train, validation, test, and train split has 67,000 rows. Each of the rows has three features. So one is just the index, second is a sentence, which is actually a tweet, and third is a label, which categorizes the sentence into either a negative or a positive sentiment. In order to use this and train our model, what we would do, we just take the sentence, feed that to the model, and just ask it to predict the next token for these words in each of the sentences. So let's get back to our notebook. Now to load this dataset, we'll be using load dataset function and dataset name. Now we run that. We can also see the structure here. And this is what we expect. Now to get the train split and the validation split, we can use ds, train and validation. So that would give us and we can look at what training dataset looks like. So this is, as we saw in the dataset on the web page. So it's got these three features which are listed here. Now to see a few of the sample, we can directly index this dataset by the index. So let's say if we want to get the sentence at the whole row at 6th index, we can just supply 6 as the index and we get the whole row as the output. We could also get a range of items, so let's say up to 10, and if we run it, so rather than getting a list of rows, we get a dictionary which is again having 3 keys that we have for one individual row, and it collates. So I'll be using this word a lot. It collates the samples into a list, so all the indexes are collated into a single list under index key, and all the sentences are collated under the sentence key in a list, and same goes for the label. Now to tokenize a data set, all we need to do, so let's just write that as the section tokenize a data set. So we need to define a function. In this case, I'll name that function as tokenize, and it will take a batch as input, and it would return apply tokenizer on that batch and on the sentence field of that batch. So if you recall, applying a batch in this case is a dictionary, and the sentence would contain a list of sentences, and passing that through the tokenizer would produce additional keys with input IDs and attention mask as the keys. And now we can actually either apply a for loop and go through the whole dataset in batch, but this datasets library also provide a utility function to kind of map a function to each of the rows of that dataset, and it can be done either in batch mode or without the batch. So in this case, I'll be applying that in the batch mode. So, but I'll be providing some keyword arguments, not like this. So in this case, I'll mark the batched as true, batch size as, let's say, 512, and we don't need this one. But what I would be doing is I would be removing the columns, all of the original columns, as we don't need them anymore after we have tokenized the dataset. So we'll be working with just with the input IDs and attention mask. The final feature was label. So these are the map keyword arguments that will be feeding to our tokenized dataset. So to feed a dictionary as parameter, as we could just pass it as such. Same for the validation dataset, map keyword arguments. And I think the naming for tokenized, I think I'll just change the name, tokenized dataset train, and I'll name this one as tokenized dataset validation. And if I run it, so that should tokenize each of these datasets in batches. And to see a row of the tokenized dataset, we can just index that, and let's say index 0, so we can see it now only has two fields. One is input IDs and another is attention mask, and all of the other fields, index, sentence, and label, have been removed. Now to look at the range of the rows, we can again pass in a range and get back an object. So in this case, another dictionary with input IDs as key, and this key contains a list of lists with each list containing the tokens for each of the rows. Now, let me just hide this one. We show hide output. Now to decode these input IDs back from the dataset, we can simply enumerate over or iterate over the entries, the range of the range that we would like to decode from, and because it returns a dictionary, we can we would just need to use the input IDs field of that, and then we run tokenized. We'll just print that out, the tokenizer dot decode, and we'll pass the sequence to that. And I'll also just, so this will be for I plus 1 index, and this will be the decoded output. So that's our decoded output, and that's the end of this code. And if we run it, we get back the tweets corresponding to these rows in the dataset, or the tokenized dataset. Now it's time for training. But before we do any training, we would like to filter out some of the tweets which are too short. So to do a filter on this dataset, this library provides another utility function called filter, and we would be, in this case, filtering. So let's say the length of the tokenized dataset currently is, so let's just print that. So these are the lengths for training and the validation dataset. Now to apply filtering, tokenized dataset train dot filter, and we want to store the result back in this same dataset. We pass in a lambda function, and we supply the len of x of input IDs, and this length should be greater than 5. Let's say, so any sentence with less than 5 tokens will be filtered out, and same we would like to do for the validation dataset. So we are running the filter, and then again we can print the length. So you can see the some of the tweets which were shorter have been filtered out, and this is the dataset that we'd be using for training. So let's now start the training process. But to do the training, we need to create a data loader that would iterate through the dataset and kind of create the batch from the dataset. So let's do that now. So preparing a data loader. Now, if we currently try to collate this data set into a batch, it just collates that batch into a list. But what we would like is to convert that into a tensor. Now, in order to kind of create a tensor from the data set, because we only have the numerical fields in the data set, so input IDs and attention mask both are kind of numerical fields. So we can actually create tensor out of that. If there were sentences in the data set, then we had to think about how to kind of collate them properly. And in order to create tensor, we can simply set the format of the dataset via another utility function provided in this dataset class called setFormat, and we are setting the format as torch, PyTorch. So we'll be using PyTorch for that. So if I just run it, and now if I tokenize dataset 0, if I look at that, so you can see now it's no longer a list, it's a tensor. But now if we try to get a range from the dataset, so let's say up to 5, it creates a list of tensors. But what we would like is to have a tensor with batch as another dimension or the first dimension. So to do that, we need to kind of have a collator function that takes the list of these tensors and create a tensor with the batch as one of its dimension. So to do that, let's define a data collator. And in this case, we'll be using a predefined collator from Transformers library. It's called data collator for language modeling. And let's define it. So data collator equals data collator language modeling. And because we are doing a causal language modeling, we'll be setting the mask language modeling to false. Now this collator, it does two things. It allows us to collate these tensors into a tensor with batch as the dimension, but it also appends a label. And for the supervised fine-tuning or language modeling, the label is just the input tensor. We'll look at an example. But because these tensors may have different lengths, and in order for an overall tensor to have of having the same length, we need to also define some padding. And to define the padding, so let's define padding for that. For our tokenizer, we need to define that padding into our tokenizer. And let's do, so the way we do that is tokenizer.pad token equals, so we're gonna be setting this tokenizer pad token, and because we use the attention mask to kind of ensure that which tokens are valid, so it doesn't matter whether we set it to end of the sentence token. So currently we just print this, we get none as the output. But now if we do print tokenizer dot end of sentence token, so that token is set, and we don't want to define, we can define, but in this case I would avoid defining a new token for padding token. So in this case we'd just be using end of sentence token as pad token. So that padding token has been set, and now it's time for us to kind of create the data loader for training and validation. So let's define data loader parameters. So let's have a batch size, and in this case we'll be using a batch size of 32. Now this has been defined on page 40 of RLHF paper. So let's just go to the PDF for some time. So this is the RLHF paper, and if we go to page 40, so you can see the batch size that they use in training. It was the 32, and this is the learning rate. Of course, these parameters depend on the specifically the learning rate depends on the type of the dataset that you have. So I'll be sticking to this batch size, but I'll be defining a custom learning rate in our notebook. So let's go back to the notebook, and now we'll define that collate function, pass that collate function as the additional key value pair, and finally we define the train data loader. So we actually haven't defined the data loader. So from torch utils data loader, and data loader being the data loader tokenized dataset train, and we pass in these parameters data loader params. Same thing for validation data loader dataset. This is val, and we pass in the same parameters. And hopefully our data loaders have been defined. Now to check the length of the trained data loader now. So because these have been batched, we should get a smaller length, so 1544 times 32, which is the batch size. So we get 49,408, which kind of matches with the length of the dataset, 408. So the batch size for the final batch is less than the batch size of 32. To get a batch from the trained data loader, we can call next to the iterator from that data loader, and then we can just print that batch. So let's just print the keys first from that batch. So now we got an additional key as labels as created by this Collator function. Now if we look at the shape of the input IDs dot shape, so we can see the this is a tensor of 32 as the batch size and 35 as the sequence length. We could also check the first value. So let's just get the first tokenized sentence. Same we can check for label. So it is labels now, not label. And as you can see, it directly matches the input IDs, but for this token and the remaining rest of this sequence, these are all mapped to 100. And we can also look at the attention mask to now get the true meaning of what it does. So you can see that up to this point, these are all the valid tokens that would be used for training, and these are all the end of the sentence tokens that are just acting as the padding tokens, and we won't be, even though they will be fed to the model, but we won't be computing any loss because the label for these tokens is negative. So label is just the index in the vocabulary. Finally, we are now ready to write a training loop for supervised fine-tuning. So let's do that now. So fine-tuning, supervised fine-tuning. Let's just define the optimizer first. So import torch, and we will be using an optimizer torch, in this case Adam with weight decay, so Adam W for that, and model dot parameters, and we'll define a learning rate. So in this case I'll just set a constant learning rate and define the number of epochs as 1. And now finally it's time to write the training loop. So here I'll just say training loop, and so we need to first set a device. So currently it's running on CPU, I think. So let's let it run for that while we are making changes. But when we do actual training, I'll switch to GPU endpoint. So torch device if CUDA, if torch.CUDA is available, else we use CPU as the device, and then we move the model to the device, and finally we write for epoch in range, number of epochs, and we set the model to train. We get the batch from the train data loader, and because the whole batch is a tensor, we can just do batch.to.device. So that will move the whole batch to the device, and then we finally pass the attention mask, input IDs, and labels to the model. The way this transformers library defines these models, so when we feed in the labels in the forward function of these models, they also generate a loss, and because they already generate these loss, I will just use them, but I'll show you where and how this loss is generated in this library. And then all we need to do is to set the optimizer to 0 grad to clear all the gradients, and then we do loss dot backward, and we'll also print the loss dot items. So that's the training loop. So let's just run it just to see if it is working. So this is still on CPU endpoint, but it's running, but it's running very slowly. So I'll do two things. I'll first stop that and change the runtime type to a GPU endpoint. Okay, and save. So that's one thing, and I'll set it to run all, and while it's running all the cells, I'll go to the transformers library, and in this case I'll go to the source code transformers loss utils Python file, and so the loss that is used is this causal loss, and the way it's calculated, so it takes that labels that are coming from the data loader that is defined in a batch. So it takes that, it applies a padding to the labels so that they are padded on the right hand side, and then it removes the first item from the label. So the way it works, let me just go to my whiteboard. So in here, these are the labels, and what we are doing is creating another padding here, another token, so which will be set to 0. It doesn't matter what it will be set to, because we won't be taking that into the loss, and we'll remove this token, and then finally we kind of left shift this sequence, and we would compare these with the logits, and we'll ignore the final logit. So that's how we kind of create the labels for loss calculation. Let's just go back to the code, and then we pass the shifted labels and the logits that we get out of the model or large language model through this fixed cross entropy loss, which is defined here. And it essentially applies the cross entropy defined in the PyTorch. And that's the loss that we are getting out when we do output.loss. And now you can see the training has been going on for a while. And initially the loss was 5. And as the training is proceeding, the loss is going down. So now once the training is complete, we can, I'll stop it for now. And to save the model, what we can do is simply model.save pretrained, trained, let's name that, save SFT model, and hit enter. So that should create, that should save the model in the save tensors format. And to load from the model, we can do model from pre-train. We can just pass the directly, so that should load the model. Now what we haven't done in this training is to validate the training, whether the model is actually learning and it could generalize to the sentences that it hasn't seen. So I'll be adding a validation stage. So I'll just copy and paste. It's quite similar to the training loop, but we'll be going through the validation data loader rather than the train data loader, and we'll be generating the output with no gradient and getting the loss and kind of taking the average of that loss. And to include this in the training, we will encapsulate train data loader under in enumerate, and then pass the, so let's validate on epoch 0, and then we do validation at after the end of each epoch. So that will be here, validate epoch +1. So if I run it now, I should run this cell also, and now if I run it, you can see, so we got a validation loss at the beginning. And so if I stop it, I'll just stop the recording, let it run. So this is the output of one of the runs that I recently ran, and this was the validation loss at the beginning of the training, so it was around 5. And if we scroll down, we can, so we can see the validation loss after the end of epoch 1 is around 3.98. So that shows that the training is actually reducing the validation loss. Now once we save this model, we can move to our next stage, which is the training of the reward model. Now the way the reward model training works is, now we're going to be utilizing the label that is available for each of the tweets, classifying that tweet as either having a positive sentiment or a negative sentiment. So we'll pass that sequence of tokens, in this case tweet, to the large language model, and we modify that large language model. We'll put a reward head on top, and rather than getting the logits out of the model, we'll be getting the hidden layer behind the logits, and then we'd be passing those hidden features from the hidden layer to the reward head to then calculate a score for each of the tokens. And unlike the previous training, where we ignored the end of sentence and used that as the padding, we will be including end of sentence token as a way for the reward model to kind of create a score for that sequence, and whether that sequence is having a positive sentiment or a negative sentiment. So that's how we're going to do this training. And to generate the loss, we already have a ground truth label, and this final score is the one we'll be comparing against the label that is there in the dataset. So hopefully it makes sense, but once we do the actual training, it will make more sense. So let's jump to the second notebook. So let's implement the reward model training. Now the initial setup would look similar. So from transformers, I'll import the auto tokenizer. So we currently won't be needing the language model. We'll define that separately. So first, let's just define the model name GPT-2, and I'll quickly run through defining this, and let's hit run. Then we would also install datasets to get the SST2 datasets. And while this is running, we can import from datasets, load dataset. Then we have the dataset name, which is SST2, and dataset, load dataset, dataset name. Okay, so dataset, we should have 3 splits as we saw earlier. Now we can again get the ds train and ds val from the dataset and let it run also. So it's loading that dataset. We got the splits. We assign them to ds train and ds val. Then we have ds. We can have a look at ds train to see everything is fine. Let's just take any random value. And now we're gonna tokenize the dataset. So this is where things are gonna diverge a bit. So let's tokenize the data set. To do that, we'll first define a reward token ID, and I'll be using tokenizer.end of sentence token ID as a reward. So as we saw in the on the whiteboard, so this is the token that we'll be using as a reward, and it will be taking the score corresponding to end of sentence token and using that for the loss. So let's just jump back. So that's the end of sentence token ID, and we can check what it is, which we I think so in the SFT training is 50,256. And now to tokenize the dataset, we will define a tokenize function. We'll again have the batch and outputs. So rather than just returning a tokenized version of the batch, I'll assign that to outputs, so tokenizer, then batch, and we'll tokenize the sentence, and we'll also be defining a score as the reward for that sequence of input IDs. And because we are gonna be passing a batch of sentences, so let me just define the outputs and score for these outputs, for the batch of outputs, and initially the score is 0 for the whole batch, and the length of the batch is input IDs. And now we would also be storing, because when we'll use it in the data loader, they will get all appended with padding tokens. So I'll also be tracking the length of each of the sequence in a separate fields. So let's say call that score index, and that will also be initialized to 0 output index. We don't need that. Then we will kind of go over each of the samples in the batch and append the reward token ID to the input IDs. So let's do that now. Range len outputs input IDs. That's input IDs, and then we're gonna append to the input IDs so that's the batch and then the sample, and we're gonna append to that the reward token ID. And same thing we need to do to the attention mask. And finally, we'll store the label that we get out of the, so that we get out of this data set. So float, and then batch label, and the ith label. And for the index, it's gonna be the last index. So we could do things like length of outputs, input IDs -1. And that will be my final output. And now, like we did for SFT training, we will define a set of keyword arguments, and we will set the batch mode to true, batched to true. And then batch size, we could define again as 512. We'll ignore the number of processes in here also, and we'll remove all the original columns as we are saving them saving everything we need in these custom columns. So index, sentence, labels are gonna be removed, and all there is left to be done is to actually run this to kind of map the data set and create the tokenized version of the dataset. Tokenized dataset train equals ds train dot map tokenize, and yeah, we'll just pass them straight like so. Let's just hit run on this. Tokenized dataset train. Let's look at one sample. Again, the same one. Now we can see that input ID is a list, and it also includes end of sentence token that we appended, and the attention mask is also 1 corresponding to that. And in this case, this sentence received a score of 0, and the index of this is the last index in this case, so that's the length of this input IDs -1. Now again, we would set the format of these dataset, set format, type, torch, and same for the validation dataset. And we'll run that. Train now should generate a tensor rather than a list, and each of the values have been converted to tensors. Now again, we filter out the tweets which are shorter than certain token length. So tokenized dataset train equals tokener. Should have done it before setting the format, but I think we should have no problem. Filter lambda x length. So length in this case of input x input ID. So this is just one dimensional. Length will be the sequence length, and greater than 5. So filter similar to how we filter these data sets in SFT training, and same we would do to the validation. So val, and we run it. Now we can check the dataset length, and you can see this has been some of the inputs have been filtered out. And because we appended the reward token, so the number of examples overall are greater. I think I should have set this to 6 because we have added one more token to keep the same number of examples. Now if we check the length, so it's similar to what we got for the training data set used for SFT training. Okay, let's now define the modified language model with reward head on top. So LLM with reward head. Rather than the underlying model is a Hugging Face transformer model, but that's also classed from the torch NN module, which is what we use to usually define the model. So what I'll do here, rather than creating a transformers model, I'll define an encompassing model as the PyTorch NN module and include the LLM as part of that, just to save us the trouble of defining a lot of configs that are needed if you want to define a Hugging Face transformers model. I hope that makes sense. From torch import NN, and then we also want to get the auto model for causal LM. Now we would define a reward head as a separate module. So reward head nn.module, and we define an init function, and it would take a config, which is the config that comes from the auto model for causal LM, just to get the hidden layer size. So let's just before we do anything, we need to call the super init function, and then we get the hidden size. Self.hidden size equals config.hidden size, and then self dot reward equals just a linear layer which maps the hidden size to just one scalar value, scalar tensor, and then we define a forward function, self hidden states. So that's the states that we get from the large language model, and we just return self dot reward on that hidden state. We pass that through the hidden states. Okay, so that's our forward function. And now I wanted to kind of also go through the another paper called An Implementation Details, just to show how we actually initialize some of the hidden layer parameters. So let's jump to the PDF, and in here I'll go to the An Implementation paper. So that highlights all the details that were used to train the RLHF training. And if we go to the page 8, and in here, so this is the way they initialize the weight of the reward head. So the way we initialize the weight, they need to be initialized with a normalized distribution with standard mean 0 and standard deviation equals 1 over square root of the D model, which is the size of the hidden state, and plus 1. So we'll be implementing this as well in the reward head, just to keep the implementation similar to the one that is used for actual RLHF training. So let's go back to the browser and define our post initialization. So def post init, and it will be a member of this class. Now we will do nn.init.normal and self.reward.weight. So they will be initialized according to 1.0 divided by np.square root. I need to also import numpy as np. So np.square root self.hidden size that we defined above plus 1, and that will be inside the square root. So that's the standard deviation of this normal. And the biases, and they don't mention it here, but if we go to this link, then we can actually see that they also initialize the biases to 0, so which is what we'll be doing as well. So let's head back to the implementation and set the biases to 0, nn.init.zeros, and that will be self.reward.bias. Now we simply call this function during the initialization state, so posting it, and that's our reward head. Secondly, we'll be defining a GPT2, custom GPT2 with reward head. So that will be the name, nn.module. We'll also subclass nn.module, then define init self. It will take model name as input, and self.llm, let's initialize that. So auto model for causal lm from pre-trained model name. So that defined our LLM, and we will also define this reward head that we created above. So reward head equals reward head self, and we'll pass in the config from this LLM. And then we define a forward function. So self input IDs, it will take input IDs, and attention mask. So these are the only two parameters that will be inputting to this model. And what we would do, we would pass these inputs to the LLM to get the transformer outputs. Self.llm.forward input IDs, attention mask, and we will also supply another parameter saying that the model needs to output hidden states as well. So we'll mark that flag as true, and I think that's all we need. So now to get the last hidden state, we can simply use the transformer output that we get and get the hidden states on that and get the final hidden state, and then we pass that through the reward head that we created, and we squeeze the final operation to remove the last value. I think I'll pass a few samples just to show you how it works. And so that's the raw reward, but we'll actually generate a sigmoid on that to kind of categorize it between 0 and 1 to keep it in line with the label in our data set. So if we run this, and let's initialize this model that we just created. So model name has already been defined, and we define the tokenizer as GPT2. Let's run this. Okay, so we forgot to call super again. I always do that. Now the model has been initialized. To pass some of the samples, let's also quickly create a data loader from data loader, and we'll be using a Collator from transformers import, which just applies the padding, but it doesn't put additional labels as a field because we won't be needing labels. So this Collator just applies the padding to the input IDs and to attention mask. And we, like we did before, we will set the tokenizer pad token equals. So now we have a choice because we will be using attention mask to keep track of which input IDs are valid, which are not. So the reward token that we append to the input IDs, the attention mask for that token is 1, but for padding tokens, it will be 0. So there is no harm in defining pad token as the end of sentence token here. Let's just initialize the data collator with padding. And so I don't think I'll be using shuffling, but we'll define data loader parameters separately. Now the batch size will be 64. If we go back to the N plus paper implementation detail and go to its page, yeah, I think we are already here. So the batch size for reward model training was 64, and that's the batch size we would be using. So let's go back. And the collator function is data collator shuffle is true, which is good. So we just pass that through data as a dictionary, as a keyword argument, data loader params. And same for the validation data loader, tokenized dataset, well, and we run both of these. Now we check the batch, and we can print batch.keys just to see what we have. So we got input ID, we got attention mask, score, and score index. And to get the first element or the batch input IDs from the batch. So this is not first, this is second. Anyway, we'll keep that. And we also check the attention mask. And then we check the score index for each item in the batch. So this is how it looks like. So we got the input IDs, we have the attention mask, and so the last end of sentence token is not clear, but the attention mask for the last token is 1, but for the rest of the end of sentence tokens, which are acting as padding token, the attention mask is set to 0, and the score is again 0 for this sentence, and the index, which is this one, the last one here, is 31. Now to decode this sentence, we can it's quite easy to do. We can again always pass this through the decode function of tokenizer batch input IDs, and so we get back the sentence along with the padding as well. Now to see the attention mask, one last non-zero element of that, so that's 31, which matches the score index. So this is all correct. Now we can actually pass the batch through the model, and let's run that. So this is running on CPU at the moment, and we can print out the shape of the outputs. And we got back the shape 64, and so that's the batch size, and 47 is the sequence length for this batch. So now we are in a position to define the training. Before we do that, we would define a training config. So let's do that now, training config. And now we did define the device. So it's we can do torch.device CUDA. Then we load the model onto the device, and we don't need to do that here, but yeah, set the optimizer to ADMW, and we'll set a learning rate 20 minus 5. And for loss, we didn't need to define the loss in the SFT training because the transformer class itself was taking care of the loss. But in this case, because we are applying a sigmoid and our labels are 0, 1, we actually can define BCE loss, and then number of epochs. For reward model, it's strictly 1, as also defined in the n plus implementation detail paper. So let's just have a look where. So that's the number of training epochs here. That's all the training configs we need. And now it's time for the training loop. So let's define that. Training loop. We first bring the model to the device, which the autocompleter was recommending us to do. And then we start writing the training loop. So for epoch in range num epochs, I like to encapsulate in enumerate and get the index also, so that we could save the model after each epoch with index in the name. And now we get the inputs by shifting the batch to the device. So those are our inputs. And for model inputs, because that one, the model just uses two of the inputs, two of the features from this input. One is the input ID, second is the attention mask. So those are the inputs, and we pass those to the model, and then we get the outputs. In this case, output is just scores, a batch of scores. Now here's the tricky bit. To actually apply the loss at the end of sentence token, which is the last token which is valid in each of the input IDs, what we need to do, we first define some batch indices. So that will just be torch a range scores dot shape 0. So that's equal to the batch size, and it will be range of that. And we use that to get the scores batch indices, and so that's the batch. Within a batch, we get the input score. So let me just step back and show you what I'm trying to do here. So when we feed the model the input IDs and the attention mask, we get outputs which are supposed to be the scores that we get out of the reward head. But the reward head doesn't just produce the single score for the entire input IDs, it produces the score for each of the tokens in the input IDs, and we are only interested in getting the score for the end of sentence tokens. So if I go back to the paper in the n plus implementation detail on page 9, we can see how the reward is generated. So for each of the tokens, token IDs, we are getting a reward, but for the end of the sentence token, this is the reward that we are interested in. So to get that reward out of the model outputs, so let me just go back to the code now. So in this score that we got out of the model, we are trying to get the score corresponding to that end of sentence token, and we know where that um, end of sentence token is in each of the sequences within a batch, as because we are storing them in score index. So I hope it makes sense, and that's how we are getting the score. Now, once we have the score, we need to define a target, and in target in our case is just inputs and the score. So that's the target. Then we calculate the loss criterion by score and target, and then we set the optimizer to 0 grad, loss to backward, and optimizer step, and we can print the loss to see how it looks like. So I haven't defined a validation function yet, so let's try and run it and see if we are getting the loss as expected. So it's currently running on the CPU endpoint. I'll change the runtime type to GPU endpoint. Hit save, so that should stop the current training, and it's switching to the GPU endpoint, and we'll run all the cells. And as those cells are running, what I'll do, I'll define a validation function as well. So let me define it here. So define validate, and this will, it doesn't need the epoch in this case because we'll just be running for one epoch. And first we need to set the model to eval and total loss to 0. Then we'll run the iterate through the validation data loader, get the inputs, transfer that to device, and define model inputs and pass that through the model. We define the batch indices and get the score from the model outputs, get the target, and generate the loss. So all of these lines look good to me. Then we get the total loss by summing the loss, and we print out the final loss. Print validation loss, this case total loss divided by length of validation data loader. So that's our validate function. I forgot to do one more thing, which is that I need to run this whole thing inside no grad. So let's just do that. Okay, so our loss is being generated. So it started out as 3 and it's getting smaller and smaller, which is good. Now we can just call the validation in the beginning of the epoch. So validate here, set the model to train, and at the end of the epoch we do the validation, and that should print the validation loss as well. So let's rerun it, and we got the error. So validate is not defined. I need to run this cell to define it and rerun it again. Okay, so we got some validation loss at the beginning, and this is the training loss. And as you can see, it's slowly, I don't think you can see it yet. So yeah, I think, yeah, it's getting smaller. I'll stop that, and to save this model, I'll just, because it's a PyTorch model, So I can directly do things like torch.save and model.static, and I'll save that as a reward model and hit save. So that should save this reward model. So that's our reward model training. Now, once the training is done, I can call validate again and get the final loss value. So it's well below the 0.693, which is for BCE loss, is the value for a random classifier. To further test it, what we can do is to generate some confusion matrix. So to do that, so I'm just going to use a scikit-learn library. So from sklearn, I will metrics, I will import confusion matrix, and that's all we need. I'll put the model in eval mode just in case it's not in that. Then I'll record all the predictions in a list and also all the labels in another. So labels in another list. Then I'll run through the validation data loader and get the input on the device and the model input. So all of this code, auto completion looks good. Then I'll make sure I'm not generating gradients, and then we are getting this score from the model and batch indices. So torch a range, so that would generate the indices for the current batch, and within the batch we are again getting the score for end of the sentence ID, which is acting as the reward ID in our case. We got the score, then we got the target. We in this case, I'm just going to leave the threshold for prediction to be at score to be at 0.5. So 0.5 and dot int. So I'm converting that to int from a tensor, torch tensor. Then we simply append all of that, but because it's not an item, it's the whole batch. So we need to use extend rather than append, which is what this piece of code is doing. And finally, we generate the confusion matrix. So if I run this code, it should give us a confusion matrix. So in the confusion matrix, the diagonal elements indicate the predictions that model got right, and the off-diagonal elements are the predictions that model got wrong. So it looks like the reward model that we trained was largely able to give the right predictions, but for some of the labels, the model where it was supposed to predict a 0 but predicted a 1, and for 43 cases it was supposed to predict 1 but it predicted 0 instead. So let me now just stop this runtime and move back to the whiteboard. This is what we have built now. Now we're going to start with our final stage, which is the PPO training. But we actually haven't defined what our goal is with this training, what we are trying to achieve. So we got an SFT model that can generate tweet-like sentences, and we got our reward model that can classify those sentences or tweets to be either having positive tone or a negative tone. Now, with this PPO training, we could do one of the two things. Either we train the model via PPO to generate only the tweets with positive tone, or we could generate the tweets only with negative tone, with the reward coming from the reward model. In our case, I'm going to use the reward model to train the SFT model so that it generates mostly positive tweets. So that's our goal. Now, before we actually go into the code for PPO, I would like to briefly talk about the mathematical framework underlying PPO and how it comes about. So I'll start with the policy gradient method. So this is a reinforcement learning method. The way it works, so let's say if we got some trajectory tau, and that trajectory is being sampled out of the policy acting in an environment. And as we act in the environment, we are gathering some reward, and the total reward for that trajectory is defined by r tau. And what we basically want to do is to find the parameter theta for the policy such that the expectation value of the reward sampled from those trajectories increase or achieve the maximum. So that's our objective in reinforcement learning. The way policy gradient works, it asks like, is it possible to take the gradient of this objective function directly? So we want to kind of take the gradient and find the direction in which this objective increases or decreases. In our case, we want to maximize the reward. So we'd like to find the direction in which the objective increases. So if we take the gradient of this objective function, we can essentially arrive at this equation. And the way, I'm not going to give the full derivation, but it uses this log trick where the gradient of the policy can be written as the policy itself times the gradient of the logarithm of that policy. Now, in order to kind of use this gradient, in the neural network, we want to define an objective, and the gradients are calculated automatically via the frameworks like PyTorch. So the way we then again convert this into an objective, and we basically want to maximize, so we remove the gradient again, and in remain the logarithm of the policy, and we basically want to maximize this objective function, hoping that by maximizing this, we would be able to tweak our parameters in a way that maximizes our original objective function. So I hope that makes sense. And now there are techniques to stabilize this whole training. Main issue with policy gradient is that this reward can vary a lot, and that increases the variance in the objective, which destabilizes the training. Now, PPO is all about stabilizing this training. One of the first things that PPO does is by subtracting a base value from this cumulative reward that we get over a trajectory, and we call that advantage. So that's one thing, but that's not the PPO trick. It's just the way to stabilize the vanilla policy gradient algorithm. So let me now minimize this and come to the RLHF objective, what it is, and what the reward looks like in RLHF. So instead of directly maximizing the reward that we get from the reward model, which is this score that we get from the reward model, where phi is the parameter of the reward model. And we actually subtract this term to generate the overall reward. And the second term basically penalizes the policy under training, parameterized by theta, if it deviates too far from the SFT policy, which is the neural network that we got out of our SFT training. So if this policy diverges too far, then we penalize that, and the beta being the hyperparameter. So that's the objective. So this is the reward that we are trying to maximize under RLHF algorithm. And the way we do that, so we are coming to the kind of the steps we take in PPO. So these are the steps of PPO. So what we do, we have a database of queries, and for a batch of queries, we ask our current policy or the current model to generate responses. Then we feed those query plus responses to our reward model to generate this score, the first term. And then we also feed query plus response to our SFT model to calculate this term. So this together makes up our reward. So that's our second step. Then in the third step, what we do, we calculate the advantage. I haven't talked about what advantage is, but so what it tells us that how good your current action is against the baseline. So if you want to define it, so the advantage equals, or I'll call it, just to be consistent with the rest of the formalism, I call it hat AT equals the RT, which is the reward of taking the action at time t, minus the total accumulated reward I expected to get from that position. So that's the value of that point in the generation. So that would be V under the policy pi at time step t. I also haven't defined what the value is, so let's define that now. So value is just the discounted cumulative reward. So under the policy pi, so that's just equals to reward at that step plus the some discount factor gamma r t plus 1. Similarly, gamma at the next time step, so t plus 2, and this will be gamma squared and plus and dots. So that would be our value function. So this is how we compute the advantage. And once we got our advantage, we are ready to do the mini batch PPO training. So we'll use a smaller batch size than the one we use for generating the responses. And in the mini batch training, we would basically use this calculated advantage to compute the loss and back propagate through the neural network to or the policy to update its parameters. And how the loss looks like. So let's talk about the PPO objective, which is the loss that we would like to minimize. But I'll talk about the objective function that needs to be maximized in here. So this is the part of the PPO objective. This is the clip objective. It's slightly scary looking, but essentially we have a ratio term, which is just the ratio of the policy under training and the old policy, which is the policy before the start of the mini batch training. So it's not the SFT policy, but it's the policy right before we start our mini batch training. And essentially what this does, it clips the objective if this policy diverges too much from the current policy. And the epsilon is just the hyperparameter by which we allow the policy to diverge from one. And so this expression comes from the PPO paper. Let's just look at the PPO paper, hope it would make more sense. So that's the PPO paper. And if we scroll down, so this is that equation. And figure 1 shows the plot for this equation. For the case where advantage is greater than 0, that means the action that we are taking is suitable action. In that case, we would like to apply the gradient only up to the point of 1 plus epsilon. But if the policy diverges, so that's the R is the ratio between the current policy and the old policy. But if the policy ratio diverges by more than 1 plus epsilon, we basically make it flat. And at that point, this whole equation evaluates to a constant 1 plus epsilon at, and the gradient becomes 0. So we basically don't apply any update. So we discount larger updates to stabilize the training. Same thing happens. So let's say if the ratio is too large, but our advantage is less than 0, so that means that action is less favorable. So we'd like to improve that action, but we only improve that if we are driving the update towards the 1. So we are not discounting this part, but if our probabilities are already small, so if ratio is small under our current policy, smaller than the old policy, then we basically don't apply any update because we don't want to drive those probabilities to 0. So that's how this expression is structured. So let's go back to our whiteboard. And that's what this expression is. And as I mentioned, the advantage is just the reward minus the value function. And if we just extend what the value function is, this is basically the reward that we get by generating each token. So this is the discounted reward, and this is the value at the end of the sentence. Now, this is the equation 10 in that paper. So if I go back, and I think there's a typo in the paper. So this is equation 7. So this is equation 10, and these are the typos. So these should have been t, capital T minus lowercase t, and it should have been -1, and same here. And then what we do, rather than calculating the advantage, in this sense, from equation 10, we use what we call generalized advantage estimation. So we calculate advantage with delta terms, summing those delta as if similar to how we sum the reward with a discount factor, but in this case, discount factor being gamma and lambda, and the delta is not just the reward, it's kind of the reward plus value at the next point and the value at the previous point. So that's the equation that we are going to be using in the implementation. We will be using generalized form of the advantage rather than this form of the advantage function. And if the lambda is 1, then this equation basically reduces to equation 10. Okay, so that's all I wanted to say about these equations. Let's move back to the whiteboard. So our final objective is the clip objective minus we are also calculating the value function. So we're going to be applying a value head similar to the reward head that we applied to the LLM. And we're going to be generating the value and estimating how that value is different from the actual value at that point. So we're going to be generating this value function loss. And there's also another term of entropy, which encourages the exploration. That means it encourages the model to produce more diverse sentences. But in our implementation, we're not going to be using the this entropy term. So it looks a bit scary, but I promise when we implement each of these advantage function, reward, it's going to make more sense. So let's now jump to our final notebook to actually implement the RLHF algorithm. So now what we're going to do, first of all, so I'm going to copy the reward model and the SFT model from my Google Drive where I saved them to here. But because reward SFT model was not just one PyTorch file, it was a Hugging Face model, so it was kind of a folder. So I zip that, and I'm just unzipping that here. So after that is done, it created a folder here with these 3 files. So that's our model parameter files and the config files. Let's minimize that. What we're gonna do, we're gonna initialize our reward model. So for this, I'm just going to copy and paste the model code for reward model that we implemented in the second notebook. So that's the code I just copy pasted. And now we're just going to instantiate that model. So model equals GPT-2. Then we're going to load the model from the state dictionary. Because we are currently on CPU, I'll also say map location from CPU, and that should load our model. Nice. So I forgot to do one thing. So this is actually our reward model, not the model. So let me just rerun that. And now we are going to define our actual model, and in this case I'll also be attaching a value head on top of that model. So model with value head, same thing what we did. I could just copy this code and paste it here, and I'll say this is my value head. I'll remove maybe I just change the value head for each output token, and in this case it generates a value rather than a reward. So I'm just gonna say it's generating a value. It's again gonna be a linear layer, and this will be value. We'll initialize similarly to how we initialize the reward model. Then But unlike the reward model, the way we're going to be defining value, its value will be from -1 to 1. So in this case, the average bias that I'll apply is going to be just 0. That's the average of -1 and 1. So that's our initialization function. Then we just apply value to that, value there. So value head is defined. Now what I'll say here is this is going to be model for causal LM with value head. So that's the name of our model with, so it's a GPT-2 model with a value head on top. So we got our LLM defined, then this is going to be a value head. So we will take value head, we'll pass in the config of the LLM, and in the forward function, we mark output hidden state, and we take the last value from the hidden state. We apply the value head to that to get the value, and rather than applying sigmoid on top of that, I want to get two things. One is the value itself, as well as I would like to get the logits. So to get the logits, lm logits equals transformer outputs dot logits. So this along with value, so this along with value is what I'm going to return. And unlike the reward model, I'll also define a function for generating the response from this model. So args, and it's just going to be generate to the LLM that we have in this model. And I think that's it really. So I'm just going to run it to define these classes, and then I'll take the model path. Yeah, one more thing I wanted to do here, it's going to be model path rather than model name, because we are going to be using this SFT model folder to get the weights from. So model path will be SFT model epoch 1 and model for causal LM to the model path. So let me just rerun it to make sure those updated changes are there, and I get an error, has no attribute of 0. So let's go back to find out what happened. So this should be value as well. This should be zeros, and this time it should work. So now we got our reward model and the SFT model. What we're going to do, we're just going to prepare a data set of queries. So let's do that. So preparing data set, and the same thing we have been doing. We first going to initialize our tokenizer, which is going to be the GPT-2 tokenizer. So tokenizer equals auto tokenizer from pre-trained, and it's going to be the model name which we defined as GPT-2. Then tokenizer, I'm just going to straight away also initialize the pad token to be same as our end of sentence token. So that's initializing the tokenizer. Then in order to get that data set again, we're going to be installing the data sets. We run this to install this, and then we're going to be loading the data sets, and in our case it's going to be the same data set that we have been using, which is the tweet dataset with sentiment as the label, and we just load that dataset. So we still got the 3 splits and the index sentence labels. Now we're just going to be using the validation and the training split from the dataset, and we run this code to initialize these values. We were doing filtering after we tokenized this dataset, but unlike the previous notebooks, we will just be taking few initial words or tokens from each of the tweets as queries. So that's going to be our dataset. So I want to make sure the tokens I take are from the tweets which are longer than certain length. So that's what I'm going to be filtering on. So let's define our filtering stage. Filtering. So let's just check the length of the DS train before we filter. So that's the 67,000 rows, and we apply filtering equals DS train dot filter. So that's the utility function. Then lambda, that's our function to filter, and in our case the length of the sentence in terms of words, so split on spaces, it should be at least more than 8. I'm just using 8, but you're free to tweak this number. So that's going to be our criteria to choose the tweet which are longer than 8 words. So I think the batch mode is by default false, and I'll just run that. Now check the length of the DS train. So if we only have now 31,000 rows. Now same kind of filtering we need to do for the validation. The DS validation dataset dot filter lambda x filter on the words, and we run that and check the length of DS val. It should have some, it's still 800 sentences. Now in order to randomly get certain words as queries from these tweets, we are going to be using random library to generate random length of queries from these datasets. So I'm importing random and also defining what the range should be for minimum token that should be present in the, so we'll be applying this random split to generate the query after we tokenize the dataset. Length equals 2, so that's the minimum. Then input max token length, and that I'll define it as 8. And now we create a range, input token length range, and that's just going to be list range of this input minimum and maximum token lengths. And just to run it, I would like to print that also. So print input token length range. So that is the range of the minimum or maximum tokens that will be taking out from our tweets. To randomly get a value out of these, I can just use random.choice to generate a value randomly out of this. And now we define our tokenization function. So tokenize a sample. The input size I'll choose randomly from the range. Let's encode a sample sentence. So we encoded the whole sentence and we only took the initial few tokens defined by the input size, and we save that in sample as input IDs. We need to also save this attention mask, so that will be 1 for each of these input IDs. So I'm just going to say 1 times length of the sample input IDs. And then rather than returning it straight away, we're going to be also storing the queries. So tokenizer.decode our sample input IDs. So these three things are what we're going to be returning from this tokenize function. And same thing, we're going to define some keyword arguments for mapping, for our mapping function to apply tokenization to each of the rows. So map keyword args, and it will be, in this case, because I'm assuming that this is just one sentence, so I'll be not applying any batch. And after I have tokenized the dataset, I'll remove the original columns. So I'll remove the columns index, sentence, and label. So I'm removing these, and then we just apply to our dataset. So tokenized dataset train equals ds-train map keyword argument, and same thing for validation. Cool, let's run that. Okay, we got an issue. Let's find out. So this should be tokenizer. Let tokenize. This is correct. Let's rerun it. This time it is tokenizing our dataset. So without the batch mode, it is slow, but we are getting there. And whole dataset has been tokenized. Now, before we do anything with this dataset, same thing we have been doing, I'm also going to convert this into the PyTorch format so that everything becomes a tensor. So torch so well, let's look at one example. Tokenized dataset train. Let's choose 6 as the random sample. So you can see the input IDs is now a tensor, and attention mask is a tensor, but query is just the sentence, so it hasn't, so this set format hasn't modified the query in our dataset. Okay, now let's also define the reward token ID, which will be appending to the query and the response generated by the model, and this reward token ID will feed this to the reward model to get the reward or score out of that model. So reward token ID equals, it will be tokenizer dot EOS end of sentence token ID. So that's our reward token ID. Now let's define a data loader. Let's torch utils dot data import data loader, and I'll say the batch size for generating the queries 32. And we also need to define a custom collator, because collators we have been using, they aim to pad all the features such that they all have the same length, but you can't really do that to query. Now let's define the collator. So collator would be collator, it would take the batch and it would return a dict, and in dict we need to have a key value pair. So let's say, so we'll have the key, and for key are coming from, so these keys are coming from batch 0, so that gives us the key. So I just took the first sample, and that sample looks like this, and we are getting the key out of that sample. So that's our key. Then the values are gonna be the list, and those lists will be d in batch, and we'll just collate them as the list. So for d key, for d in batch, so that will make them into a list for those keys. And that's really the collator function, and I'll show you how it looks like. So now we just define train data loader equals data loader, and we apply this collator function. I'll also set the shuffle to true, same shuffle true. So those are our train data loader and validation data loader. So let's run this, and we got the error. and the error is this supposed to be in Pascal case. So I'll just change that, and this time it should work. To get a batch, we just do next and iter on that. So let's say train data loader, and we print the batch. So this is how our batch looks like now. For input IDs, we got a list of tensors. So these are the input IDs. And then we're going to have an attention mask. That's another list of tensors. So we are basically collating all of the input IDs and attention mask without padding. And why we are doing it is because we would like to generate some responses for each of these queries. And in order to generate responses, we would be doing it one by one. So I want to avoid, so because we'll be appending things after this as we generate the responses after the queries. So we have two choices, either to generate the responses one by one, which is makes the code looks easy, or we append these queries so that they are of the same length, append them from the left side, and then we generate the responses. So in this case, I'm just gonna do it one by one rather than doing it in batch, and therefore we are not kind of appending any padding tokens to make them of the same length, because we are not doing it in the batch. So I hope that makes sense. And we also got a query field, which is the decoded version of the input IDs. So let me just hide this output, as this is fairly big. And now I'm going to define how to kind of generate what the length should be of the generation given a query. So similar thing how we did for sampling the queries, we're going to sample the responses. So I'll define a minimum length of the output or response as 5, and output max length as 16. So let me now define generation keyword arguments. And the way I'm going to define them and where I'm getting their values from, I'll just leave a link. But these are the best kind of the recommended values for generation of responses when we are generating the data for PPO training. So do sample. In this case, we do want to sample, and I would also define a pad token ID to tokenizer dot just to token ID. So once these values have been defined, so now I'll leave a link here of where I got these values from. So if we open this link, so these are the recommended keyword arguments for PPO training. And what minimum length does, if the model produces end of sentence token, then it doesn't ignore that. It disables the top K sampling. Then we also disable no nuclear sampling, and we do sample from the model as we generate the response. And the max new tokens, so we define those output. So let's go back. So we define these output minimum length and output maximum length, and we're going to be using these to generate maximum new tokens. So let's run this one and define sample generation. And so in this case, generation keyword args equals keyword args, and we're going to be setting that max new tokens, and I'll take that from random.choice. So let's just set that separately. New tokens equals random.choice, and list range from output min length to output max length. And that's the max new tokens. And then I'll create a query and tokenize that. Tokenize so hi this. So let's say this is our query. Then let's run it to see how the encoded query looks like. Then we feed the query to the model.generate and input IDs equals. So because this is a list rather than a tensor, so we're going to be converting that into a tensor, and it will be sample input IDs, unsqueeze, attention mask, tensor torch, unsqueeze, and the generation keyword arguments. We are using unsqueeze because so that we kind of add a batch dimension to these input IDs and attention mask, and then we're going to squeeze the final result to remove that batch, and that's going to be a query response, and we just print that query response. So let's see how it looks like. So the first three tokens are same as the input IDs, and the remaining tokens are the ones that we generated. And if you want to decode that, so tokenizer.decode query, you can just pass query response to that, and hi, this is bound to cause a few tears to cap off this one. So that's the generated response that we got out of the model given this query. We can also get the score from the reward model. So let's do that now. So with torch.noGrad query response score equals torch. So we didn't need to use noGrad for model.generate because that already applies torch.noGrad. So now to get the score, we need to also append the reward token ID to the query response. So, and we need to convert that token ID to tensor as well, and along the dimension 0. I think it's by default the dimension is 0, so we don't need this part. I'll just get rid of that. And so I unsqueezed it, or I'll just unsqueeze it all together, and I'll generate an attention mask equals torch.onceLike query response score, and d type is going to be torch.long. Then we simply feed these two values to our reward model query response score and dot unsqueeze and attention mask dot unsqueeze, and we will squeeze the final result. So this will give us the score for each of the tokens, and we are interested in the score for the final token, which is our reward ID token, and that's the score. And we run that and we got our score. So because this is not expressing a positive tone, so the score is closer to 0 rather than to 1. Then let's do the same for, let's generate for the batch, so batch generation. So this was for just one sample. Now we're going to apply the same thing to the entire batch. So we're going to generate the responses for the batch and the scores. So let's do that now. So before we do that, I would also like to define the device. So it's going to be CUDA if torch. So currently we are on CPU endpoint. Then we're going to be transferring these models to device. Same thing for our reward model to device. And then we're going to get the query tensors from the batch, input IDs, and query attention mask with masks, because those are the masks for the whole batch, and attention mask. Then we're going to create some lists to store these tensors that we're going to be generating for the batch. Query response tensors and score tensors. Let's create a for loop to go through each of the queries. As I said, we're not going to be feeding the whole batch into the generation. Instead, we'll be generating one by one. And the reason I'm doing that, I want to avoid padding the queries, which ordinarily need to be paired from the left-hand side for generation. And then we'll have to remove that padding. So to avoid all of that and to make the code more readable in this case, I'm just avoiding using padding altogether, and we'll be generating per sample rather than per batch. So let's move this query to device, and same thing to attention mask to device, and then we are defining a generation length, so new tokens. Finally, we pass these query and attention mask to our model for generation, and then let's isolate the response from the query. So response length would be length of the query response minus length of the query, and we would use that to append to our response tensor. So response tensors dot append query response sampled from response length, and then we append to our query response tensor, not this one, but just the query response. Then let's generate these scores. So torch.nograd query response score equals torch.cat query response, and so I'll be concatenating the reward token ID ones like query response score and feeding that to, I'll also need to transfer these to device. I think this will automatically be transferred because we are using ones like. Now we get this score and we store that score to our list, score tensors. But before we do that, we also would like to scale the score. So currently the score is between 0 and 1, but we'd like to score it so that it becomes from -1 to 1. And with that, let's also just decode the generated response in response tensors just to see how they look like. For response tokenizer dot decode response. So those are our responses, and we simply print that those responses. So print. Let's try and run it. I think it's a good time for me to switch the device to GPU. And we got our responses from the queries. Before we proceed any further, I would now change the runtime type to GPU endpoint. So let's just change that to T4 GPU and run all of them again. So that should take some time, but while it does that, let me go back to the whiteboard to kind of describe where we are. So far, we generated some sample responses given the query. So let's say X is the query, Y are the responses. And for each of those query and responses, we got the score out of our reward model. Then in order to get the full reward, I would like to get the second term. So what I'm going to do is pass the generated response for the query to the current policy as well as to the SFT model. So far, all we have is the SFT model. And what I'll do now, I'll create a copy of that model and one model will be actively under training and other model will be our SFT or reference model. So let me do that now. So let's go back. So we got an error here, and the error is we need to move this one to the device rather than the overall operation. Then so query response is already on GPU. Then the new tensor that we are creating out of the reward token should also be on the device, and then we concatenate the two. So let's run this again. This time it should work, and it worked. So as I said, let's just define the SFT model. So from copy, and the way I'm going to do it is just by creating a deep copy of the current SFT model that we have. So SFT Model will be deep copy of our model. Let's run this one, and we got our SFT model. Now, in order to generate the, so let's go back to the whiteboard. So in order to generate these probabilities from the current model and the SFT model, I'll have to pass the query and responses to both. And to save us some time, now because we don't have to generate, so we don't have to worry about padding from the left, so we can actually feed the entire batch to the policy and SFT model. But in order to do that, we have to actually do padding. So let's do that. Go back. So let's define a collator from transformers import data collator with padding. So that's going to be our collator, and let's initialize that, and that's our collator. Let's run that. So let's now try to collate this query response tensors with the data collator that we just created. So I'm going to say input data equals data collator, and it's going to take a list as the input, a list of query tensors, and each of those lists will have an object with input IDs and attention mask as keys, and those are coming from for IDs in query response tensors. So those are coming from there, and once the collation is done, I would also like to move that to device. And in the IDs, I'm just going to pass the IDs. So that's these are the input IDs. And for attention mask, I will define ones like IDs, and that should automatically create a tensor of all ones for these IDs. And just print this to see how it looks like. And as you can see, it's got query, some response, and then the padding as defined by our padding token in the tokenizer. So those are the input IDs, and the attention masks are 1 for query and response and 0 for the padding, so that we don't generate loads for those tokens. Okay, once that's done, now we are kind of ready to compute a reward. And in order to do that, I'm going to create a function that would take this input data that we could generated and query tensors and a response tensors, and then finally these cotensors. Those are the lists that we created when we were doing the generation. So it takes all of those and it generates the reward. So essentially we are planning to get logits out of our policy and the logits out of our as reference model. Let me go back. So logits values. So because our model generates both the logits and values in its forward function. And I'm just going to pass the input data to that. Same thing for reference logits. And in that case, we don't really care about the values. And this will come out of our SFT model. So logits are unnormalized probabilities. Now to generate log probabilities, we simply can apply a log softmax to our logits. Same thing to ref logits. So these autocompletion suggestions are looking good. Let me also remove the last items from the sequence. So last item from the sequence. And why we are doing that is because we want to align our labels. So let me just define what our labels are. So labels are just the input data and input IDs. And they will start from 1, 2, and go up to the end. So these logits have a shape of batch, sequence length, and vocab. And the labels have the shape of batch, and sequence. So now I kind of align them, the generated logits with labels. So let's me go back here. So by removing the last item in the logits, I am ignoring this item. And in the labels, which is the input data, I'm ignoring this item, so that we are aligning these tokens and logits. And now we would like to get the probability or log probability for each of the tokens in the sequence, so that we get the probability for that token to get this value. So let's go back to our code. So yeah, we align them, and now in order to get the probability for those tokens, we will do torch.gather. So it's gonna take log probability that we have, and so dimension here would be the 0, 1, the final last value. So we'll be gathering from that dimension, and what we'll be gathering are the labels, and then we'll be unsqueezing the labels for it to have the same shape as the log p values that we have. So these have the shape of this, so we unsqueeze this to add an additional dimension at the end. And once we then gather, we squeeze the result, we remove the final dimension, and that would leave us with just the batch and sequence. So I hope that makes sense. And same thing we're going to do for our ref probabilities. So ref log p equals torch.gather ref log p along second dimension, labels, unsqueeze, squeeze. Then, so because these are already in log, so to compute this term, all we need to do is subtract the log of pi SFT from log pi, our current policy. So let's do that. So, and I'll call that as KL divergence, so log p minus ref log p. And now I need to define this. I need to define this beta. For this training, I'll set the beta to 0.2, and we will get the rewards without the score as beta. So it will be minus times KL. Now, because this rewards include both query and response, so we'd like to only apply the reward to the response rather than query. So to do that, we'll be creating a mask and we'll be using the attention mask initially. So input data, we can just get the attention mask. So that's our attention mask, but we'll create a mask from there, and that will be zeros initially. So zeros like the attention mask, and we'll also be applying a shift to that. Same thing how we did to the input ID, so we shifted them. And so that's the initialization, and I would assign all the values in masks as the attention mask. So initially, wherever the attention mask is 1, it will be just shifted version of the attention mask. And now I would like to zero out all the places where we have query. So in order to do that, I'll iterate through the query tensors. So query tensors, so that's the batch size. Length of query tensors is the batch because it's the list of query tensors, and the size of the list being the batch. Then start value would be length of the query tensors at that batch, and -1. So because it's an index, and the end value would be start plus len of response tensors. And all I need to do, because its masks is already set as 1 in every place, so we need to set it to 0 up to start, and zeros from j and up to starting from end. So that's our masks. Then in our rewards, we are going to set the rewards for jth batch and -1 on the last index. We are going to add the score tensors j, so that we got, so rewards initially is this term, and now we are adding the score that we get at the end of the sentence to fully compute both the terms. And now we're going to set, using the mask, we're going to also set all the values which are outside of the mask. Masks equal to 0, and so we're basically applying the masks to the rewards. And finally, the values are the ones we calculated here from the model. So we'll be applying masking so that we don't worry about the values that are outside the masks. And then we just simply return. So what we're going to return, so we'll be using it later on as well. So that will be the old value before we start our mini batch training. So we'll return the log p, we will return the rewards. And because values haven't been aligned, similar to how we are kind of removing one element, so we need to remove one element from values as well. So let's just remove that final value from the values, and we also return the masks. So these are the values that will be returning from our compute reward function. And let's run it to define it. And now let's try and calculate. So we are getting log probes, rewards, values, masks out of compute rewards, input data that we created from the Collator with padding, Then we are just simply feeding query tensor, response tensors, and score tensors. Now we simply print rewards at batch 0, print input data just to see how everything looks like, input IDs for batch 0. Also print the attention mask also I would like to print, so input data attention mask at batch 0. So let's print all of these, and we got an error. The error is removing s, so it should be torch.nograd. And let's run it again. So now we got everything computed. So if you look at our rewards, so in this case, because the SFT and currently the model and SFT model are same thing, so KL divergence is 0, and all the reward is the just the score that we are adding here, and that's at this location, and which should be the final point along this sequence, and the mask is 0 for the rest. So let's also print the other values. So let's print the masks also, as well as the values for batch 0. So as you can see, the masks is 0 for the query. In this case, the length of the query was 3, and for all the response tokens, the mask is set as 1. And the values, so values are coming from our value head in the model, and that also has been masked. So the values are 0 for queries, which are input, and for responses, we are getting some values, and then it remains 0 for the padding tokens. So that all looks correct. Now it's time for us to compute the advantage. So compute advantage. I think this and the loss computation are going to be the most tricky parts of the entire code. So let's go over it slowly. So first what I'll do, I'll define a compute advantage function, and what it will take are the rewards, values, and masks, which we are getting out of our compute rewards function. And then it will use that generalized, let's go to our whiteboard. So we need to kind of create this sum to calculate the advantage, and we need to define these gamma and lambda parameters. So let's go back there. So we'll have last generalized advantage estimation as 0.0. Then we have the advantage reversed, so we'll be computing it in reverse from the end of the sequence to the beginning of the sequence. Let's also initialize our sequence length, so that would just be rewards dot shape and the -1. So if you look at the rewards, so -1 rewards is just 2-dimensional tensor, and the last dimension is the sequence length. Then we define our gamma and lam, so that's the lambda, and gamma in our case we'll just set that to 1. So that means we are not discounting the reward as we cumulatively sum them. And for lambda, we'll be setting that to 0.95. So these are the two hyperparameters. Then this is what we're going to do. We're going to, in reverse, iterate through the sequence length. So reversed range sequence length, and the next values, so it should be length, and next values are the values in the previous iteration. So those will be either values for the entire batch, t+1, if t is less than sequence length minus 1, else it will be 0. So it will be initialized to 0 in the first iteration. Then we have a delta. So those deltas are going to simply be rewards for the whole batch, and the t value plus gamma times next values, and then minus values t. So let's go back to the whiteboard just to show you where this delta is. So that's this delta, and it's simply reward plus gamma times the next value minus the current value. And that's what we kind of defined here. So that's our delta. And now we calculate the last generalized advantage estimation, and that will be delta plus gamma times lambda times last JEE, and that's why we were kind of doing it in reverse, so that we could utilize the last value for calculating the previous value in the sequence. Let me just go back to the whiteboard again to show you. So we are kind of calculating the advantage in the reverse order by first calculating the last value, and then we apply the lambda gamma to the last value, and we sum the current delta to that value. And that's our last generalized advantage estimation. And then we simply save that advantages reversed list dot append and last generalized advantage. So that's our advantages in reversed order. And in order to get the tensor for the actual advantages, we would like to stack all of those items in the list. So stack advantage reversed. So let's just go to advantage reversed. And because they have been appended in the reverse order, so we need to reverse them back, and we'll be appending them in the along dimension 1. So first dimension is the batch, and the second dimension is where we would like to append them to create a sequence. And finally, there is one more thing we need to do. We need to whiten the advantages. So I haven't talked about what whitening of advantages mean. So let me just pass it through a function called masked whiten, and it would take advantages and masks as input, and it would return the whitened advantages. So this advantage whitening comes from the N implementation detail paper, where what it does, it simply calculates the mean and the variance for the values. In our case, it's the advantages. And once we get the mean and variance, then we kind of normalize with respect to those values. And then because we shifted the mean in the whitened value, we then shift back to the mean. So we are not changing the mean, we are simply just normalizing and then shifting back to the mean. So that's what we mean by whitening the advantages. So first we need to define a function to compute mean, and in our case it will all be masked mean, because we will only be computing the mean with respect to tokens which are unmasked. So but to calculate that, we would simply multiply the two and sum them, and then we would sum the mask to calculate the mean, and then we calculate the masked variance. So values mask, and to calculate the variance we would need the mean. So we'll call the masked mean function that we just defined above to get our mean. Once we got our mean, we can then compute centered values. So values minus mean, and then we simply return masked mean centered values to the power 2. To compute the variance, we have to raise to the power 2. So we'll simply take the mask mean of those centered values. And finally, we will define the function masked whiten that we called here. So masked whiten, and it would take the values and mask, and it would get the mean and variance by calling masked mean and masked var functions. And let's get rid of this line for now. Then we would simply get the whitened advantage. So that will just be the values that we originally have minus the mean. And so we divide that with the square root of the variance. And to divide that with the square root, there's a function in Torch called r square root. So that's stand for reciprocal of the square root of variance. And we would add some very small number, epsilon, to avoid dividing by 0. And before we return, we would sum the mean back, and then we return whitened advantages. And that's the function. Then before we return out of the compute advantage, we would like to also define a variable, which I'll come back to when we actually dive into the loss calculation, so that it will simply be advantages plus values. And these are the two things that we'll be returning. So advantages and returns are the ones which would come out of the compute advantage function. So let's try and see if it works. So let's try to get these values, compute advantages, compute advantage, feed in rewards, values and masks, and then we simply print out the advantages. So this function is working. Now let's come to our final piece in the PPO steps. So let me go back to the whiteboard again, minimize this one, expand our steps, and that's the mini batch PPO training. So let's define this PPO training. So this is where the training would happen. So we would also need to define a training config. So let's go back, and I'll put a bigger heading with mini batch PPO training, and in this I'll create a subheading training config. Okay, so I'm just gonna choose a learning rate to be 1e minus 5. I think in the an implementation detail paper, so let me go back to that paper. So on table 7 we got some PPO hyperparameter, and the optimizer here is AdamW, and the learning rate. So because learning rate depends on the model size and your data set, so I would choose a learning rate which suits that, but I'll be using AdamW. I won't be using any scheduler, so I'll keep the constant learning rate. Then the batch size, because we are working on Collab, which has limited GPU VRAM, so we'll be working with 32 batch size, which is what we've been using. And the KL penalty, I think we defined that 0.2 currently, and gamma and lambda are as defined here. And for the mini batch, because we are using 32 for the batch size, we'll be using 4 as the mini batch size. So let's jump back to the code. So that's our learning rate, and the optimizer equals torch.optim.AdamW, and it would be model.parameters, and the learning rate equals learning rate. So that's our optimizer. Now, in order to iterate through the batch with a mini batch size, I'm going to first do some permutation. So what I'll be using is random permutation. And if I just apply the batch size, which is currently set to 32, it would generate me a random permutation of that. So I'd be using this, a permutation, to kind of get a random slice of size mini batch size to iterate over a batch. So let's define the mini batch size equals 4, and we would be also running this mini batch training for 4 epochs. So PPO epochs, I'll be setting that to 4, and then I'll be defining some clip range. So those are going to be the epsilon. So let me just define them, and then I'll go to the actual place where they are defined in the mathematical formula. So let's go back to the whiteboard. So those are these epsilon values for the clip part. So we define those clip range, and then we're going to be also defining a loss coefficient for our value loss, and that's the value. So in our final clip loss, let me just move that out of the way. In our final PPO loss, C1 is that value we just defined. Let me go back. So that's this value. Then let's define the mini batch train function. So mini batch train, and for epoch in range set by PPO epochs. So I'll go over the batch PPO epochs time. So 4 times in this case with a mini batch size. So let me just get the batch indices equals a random permutation of batch size, and then I'll start the PPO batch training. So for start in range 0 to batch size in this type of mini batch size, and the end would be start plus mini batch size. Now, so those are the indices in the batch indices which we get randomly generated, a permutation of the range from 0 to 31. So let's just get the random slice out. So mini batch indices equals batch indices and the start to end. Now we need to define the model input for mini batch. So MB model inputs. So those are going to be again the input IDs. So that would be input data that we already have, then the input IDs from there, and the mini batch indices. So mini batch indices. So that's the input IDs. Then the attention mask we can define similarly. So that's our mini batch model inputs. And now all we need to do is to pass these inputs to the model, so model and MB model inputs, and what we get out are logits for the mini batch and the prediction for our values. So those are the 2 things that we get out of this model with value head. Now, similar to what we did, we're going to normalize the logits that we get with a log softmax, a torch.nn.functional.log softmax MB logits. And so we'll be taking the softmax along the final dimension, and dimension equals -1. But before we do that, we would also be getting rid of the final value. So we would remove the final value as we don't care about what the model generates for the last token in the response. Then in order to calculate the probability that model assigns to the token, we're going to do something similar that we did before. So we're going to gather the log probes. So those are going to be the log probability. So torch.gather MB logits along the dimension of vocabulary, and from the MB model inputs, input IDs, and these are going to act as the labels, but we need to shift them. So we'll remove the first item from these labels, and we'd also need to match the dimension. So this is being the 3-dimensional tensor, and this one is just 2-dimensional. So we're gonna need to do unsqueeze along the last dimension, and then we're going to squeeze the result back also along the last dimension. So this code is essentially similar to the one we use to compute the log probability for the model and the reference model. So we defined the labels, and we had to shift the labels, we had to shift the logits. So it's essentially the same, but for the mini batch this time. So now we got these, and we're going to get some losses out of a compute loss function, which we haven't defined yet. But what it's going to take as input is going to take the log probes that we get out of the compute reward function indexed on the mini batch indices. It will also take the values. Again, we get these from the compute reward function. Then it's going to take the MB log probes that we are calculating above. So these values, and because these are already mini batch, so we don't need to supply mini batch indices, and also the MB value predictions, then the masks that we get out of the compute reward function indexed on mini batch indices, then the advantages indexed on mini batch indices, and finally the returns that we also get out of the compute advantages function indices. So these are all the values that I'm going to be feeding into compute loss, and loss will include the loss v. Loss v is just for monitoring purposes. All we need to do is to set the optimizer to 0 grad and loss to backward, and optimizer to step to update the model parameters, and then we're just going to print the loss, and that's the total loss. So loss.item, and at the end of this mini batch training, we're going to say that mini batch training finished, just to see how the training is progressing. So now let's define the compute loss function. So define compute loss, and as I said, it's going to take all of those values. So I'll call those all log probes and values and log probes. So these are the mini batch log probes and the v predictions, value predictions, then masks, advantages, and returns. Now to get the so essentially in this compute loss function, we are, so let me go to the whiteboard. So essentially we are trying to compute these two terms. So we're not going to be computing this one, the entropy term. We're going to ignore that, as it only encourages the model to kind of do exploration and produce more tokens, which might actually end up destabilizing the training. So we are just avoiding entropy. And so what we want to do, we want to calculate this ratio because we have log probabilities, but this is without the log. So we're going to have to take the difference of the log probabilities and then apply the exponential operation to that to get this ratio. So let's just define this ratio. Go back to the code. Ratio equals torch.exponential log probes minus all log probes. That's the ratio. Then we're gonna define the PG loss 1. So that's the loss without any clipping, loss 1. So it will be ratio times the advantages. And then we're gonna define the clip loss. So PG loss 2 equals torch.clamp to clamp the value ratio, and the values is going to be between clip range ratio and 1 plus clip range ratio times the advantage. So we got these two terms. So let's just go back to the formula to see where we are. So essentially, we calculated this first term and the second term, where we are clamping the ratio to stay in between these extremes and then multiplying with the advantages. And we are taking a minimum of this. So let's go back to the code. So let's define the PG loss. So PG loss would be torch.min, min of PG loss 1 and PG loss 2. Now if we go back to the whiteboard, in this equation, so we implemented the minimum operation, and because this is a clip objective which needs to be maximized, but in our PyTorch training we need to define the objective that needs to be minimized. So we'll be actually applying a minus sign, and for expectation we'll also need to take the mean of the loss. So let's go back to the code. So we do these two things. We'll take the masked mean, and that's why we've been passing the masks to these. So masked mean of this, and we need to take a minus of that, of this value, and we need to supply masks. So that's one way of doing it. Or what we can do, we can just put negative signs in front of these, and then we get rid of this negative sign here and change that to torch.max. So both of these implementations are identical. So I'm just going to stick to this implementation in this case. So that's our PG policy gradient kind of loss. Now we need to define the prediction loss, and that would simply be V loss equals, so V prediction from the mini batch, and then the returns that we are getting out of the advantages function. So because advantage is kind of the, let me go back to the whiteboard. So because the way we calculate the advantages is by subtracting, so let's ignore this expression for now. Let's focus on this expression. So by subtracting the value from cumulative discounted reward, in order to get the true value, we add the value in the advantage to get the true value for the cumulative discounted reward, and which is what the true value is supposed to be. And that is what we defined as returns, and that minus the V prediction, that would make up our value loss. So let's go back to the code. That's what we've done here. So V prediction minus the returns, and that's our loss. Then we simply sum the two to generate our final loss. So PG loss plus V loss coefficient that we define in here times our value loss. Now we can actually return the two. So those are the two losses that we are returning out of the compute loss function. But to make this training, to stabilize this training, I'm going to set an additional constraint, and that's going to be constrained on the ratio. So the average ratio, let's say, so that's going to be the masked mean of the ratio with the masks. So this ratio, if this exceeds a ratio threshold that we haven't defined yet, then I'm going to ignore all the losses. So PG loss times 0.0 and the V loss set to 0.0 and loss equals loss 0.0 times 0.0, and I'm just going to return. So all of these tricks that PPO uses and the one we are using are done to make sure our training remains stable. And now we define what this ratio threshold is. In my case, I'm just gonna set the ratio threshold to 10. And let's try to run this code to kind of define these two functions. So let's just try and call this function that we defined. So mini batch train. And we got some error. And the error is while passing these value predictions, we should have also excluded the last item, like how we are excluding the last items here. Same thing we need to do to our predicted values. With that, let's redefine the function and call it again. And we got another issue. And this issue is related to VLOS, so we forgot to apply a mean to our loss for values. So let's do that, masked mean and masks. And now let's redefine both the functions and run it again. And this time we are getting the loss and all the 4 epochs are finished. Okay, so that's our training on one batch that we generated from our policy model. Now let's define the full training loop, which would include the generation, the reward computation, advantage computation, and finally this mini batch training. So let's do that. So I'm going to say train RLHF. So that's going to be a final cell. Actually, we're gonna also be validating our train model. So just we are nearly there. So number of epochs, in this case, I'll just train it for 1 epoch, and for epoch in range num epochs. Then I will generate a batch for in train data loader, and we're going to generate some responses. So generate responses. We'll take the query tensors equals batch input IDs and query attention masks. Again, we get them from the batch attention mask. Then we're going to define those 3 lists to store the response tensors and query response. You know what? I'm going to go back to the code which we already got in the previous cell. So this is what we are going to copy and paste there. So let's copy. We go back. And we paste it. We need to fix the indentation. Let me just see if we got everything we needed. So we are getting this core, we are normalizing this core, and then we are appending that to score tensors. So we got this core. Now we need to compute the reward. And for reward, we also need the KL divergence. So we're going to define our input data with padding So we're going to be using our data collator for padding, and it's going to take a list as input and input ID. So it's mostly the copy paste from what we did above. And once like ID is in query response tensor to device. And so this looks correct to me. So this is going to be a dictionary. Let me fix the formatting. So this is our input data. We use that to compute the reward. So this is the compute reward. We feed in the input data, query tensors, response tensors, and score tensors. And once we got our rewards, log probabilities, values, and masks, we're going to be using them to compute the advantages. And it's going to take in rewards, values, masks, and it's going to return us advantages and returns. So this is our rewards and advantages. And finally, we're going to do the mini batch training. So mini batch train, and after the epoch, we're just going to print the print f epoch +1 finished. So that's the whole code. I hope it made sense. So let's run this code, and we got an issue. And the issue is, it's quite silly actually, what I should have done. So once we calculate the score for each of the query tensors in a batch, we should be doing this part outside of the for loop here, and then all of these would be computed for the whole batch. Same for the training, and now it makes sense. So let's rerun it, and we got another issue. So I put these print statements. I'm gonna remove these, and the issue is actually quite simple. So we made a typo here, so it should be advantages, and that's what is going to go in mini batch train. So if I run it again, it should work, and that's our full PPO training, and it's going to run for the whole epoch. So I stopped the training and I disconnected the runtime, and before I run this training any further, I would like to implement the validation function. How do we validate the model after the PPO training? So let's just define that first, validation. And so we have been having a validation dataset that has about 807 rows after filtering. So that's defined around here. So that's the dataset validation. And so we created this, but we haven't actually used it so far. So now, so because I ran that, it's reconnecting to the validation, to the endpoint, and nothing is defined at the moment, but we'll just ignore this for now. We'll run the whole notebook after we finish implementing. And now what we want to do, we would kind of generate a list of random lengths that we would like our trained model to generate for the validation dataset. So the length of this list is going to be the length of validation dataset. Then from for I in range length to tokenized dataset validation. And what I'll be doing, so I'll for each of the rows in the validation dataset, I'll randomly choose between the range of output min length and output max length. And why I'm doing it all beforehand, before we actually feed the query for each of the rows in the validation dataset to the PPO model, I want to first feed the same set of query with the same output length to the SFT model and get some generation out of that, and have the score model produce an average score for those. And then after the PPO training, we would like the new model to also generate for the same lengths, and then we calculate the average score on that to find out whether the PPO training has helped improve that score. So that's our validation gen lengths, and we're going to be assigning to each of the rows. Let me just run it from the beginning, run all. And while this one is running, I'm going to create a new cell. Just going to list out some of the values in here. Let's say first 10 values. Then let's define the validate function. And we're going to collect all the scores that we generate from the reward model for the generated responses. So for B and batch in enumerate validation data loader. First step, generate responses. So again, it's kind of the similar code that we have been using. Input IDs, query attention masks, attention mask for I in query. Then so once we got a batch, then we're gonna iterate in the batch for each of the query in enumerate query tensors, and we're gonna shift the query to the device. Same thing to query attention mask. Then we're going to be defining new tokens. Those are going to be the length that we get out of the validation gen lengths, and we're going to create this index, and it's going to be length of this query tensors. That's our validation gen length, and we're going to set this into the max new token of generation keyword arguments. Then we generate the responses along with query. Let's go back. And we started seeing some losses here. Let's stop this for now, and we would like to run our validation first. So we're gonna run the validation, and th lengths. So these are our validation lengths. Then we do query response score to append this query response. So concatenate query response with torch.tensor reward token ID. This needs to be transferred to the device. So this is the input that would go to the reward model. To feed that, we're also going to define the attention mask. So attention mask equals torch.onceLike query response core. So that's our attention mask, and we feed this to our reward model, and we scale this core. So 2 times core minus 0.5, and we append that to our list. Scores.append score.item, and finally we after running this for the whole batch, we generate the average score and print that out. So average score equals sum of scores divided by the length of scores. And we call this validation function, so I'm going to call it separately validate. So we made a typo in here, so it should be for I comma in query, I comma query in enumerate. So let's rerun it. I got another issue, and that's with some append having 3 P's. And now it should calculate the score. Let me just stop this before we proceed further. Let's just create another cell here. So I'm just going to reinitialize my SFT model. Let me go up, copy the code for initializing the SFT model. So that's this one. Go down, paste here. So let's run this too. So this is our SFT model now, and we're going to be calculating validate on our SFT model and running it. We get an error, and the error is I need to actually shift this to the device level. So when I reinitialize, and now it should work. So this ran for 1 minute 48 seconds, and we got an average score which is fairly close to 0. So the model is generating sentences which are on average both having positive and negative sentiments. Now what I'm going to do is to run the entire notebook to get this validation score after one epoch of PPO training is finished. So let's rerun all the cells in this notebook, and I'm going to pause the recording. So the PPO training has been running, and I'm just waiting for one epoch to be finished. Then I'll generate these lengths again and run the validation on the newer model, and then I'm going to reload the SFT model and run the validation on that. So let's wait for this to finish, and I'm going to pause the recording for now. So now our training is over, and I had to do a few more runs before I got to these results. And basically I also added a line where I'm saving the new PPO model. And after the training, this is the score that we got out of the model. Essentially what's happening here, before the PPO training, the model is generating tweet-like sentences, and it is generating sentences having both positive and negative sentiment. Therefore, the average score is close to 0. But when our one epoch of training is finished, it tends to generate sentences more which are having positive sentiment. So that's what this higher average score means. So that's all I wanted to cover. So what we could have done better, I think one area which was quite annoying for me was having to generate the responses for each sample in the batch. So the way we currently set up the implementation was we got a batch out of the training data loader or validation data loader, and then we were going through each of the samples in the batch to generate the response. But we could actually have padded those queries from the left and generated the responses. So that's one thing that the code lacks. And I haven't done enough experimentation to arrive at the best hyperparameter value. But as you could see, the PPO training was stable. So we did get improvement in the average score after one epoch of PPO training. So that was a good thing. But I think the hyperparameters could certainly be optimized. So these are the few things that I think the code is lacking, but it's roughly there. And I'm going to put some links in the description of the video to these notebooks. So feel free to run them on your own. In the future, I'm planning to do more deep dive videos like this. So things like GRPO, which is another reinforcement learning technique, and how to distill a large language model into small language model. So those are kind of the topics that I'm planning to cover. And if you like this video, please leave me a thumbs up. And the best thing you could do to support this channel is to share it with your friend or someone who might find these kind of deep dive videos helpful. So please share with them. Finally, thank you for your patience and sticking around to the end. Bye for now.